Hi there, welcome to this lecture series on matrix algebra. This is lecture 25, part 2. The topic is applications of using the powers of matrices. In this part in particular, we'll cover the Fibonacci numbers. First, a brief introduction to this Italian mathematician and Leonardo Fibonacci. This is a picture of him. He is famous of writing a book called Liber Abaci. He introduced the Hindu Arabic decimal number system into Europe to replace the Roman numbers, and that was extremely useful for merchants to calculate. So in particular, how to relate the price of goods in various currencies and calculate your profit and your loss. However, he is most famous for a sequence of number named after him called the Fibonacci sequence. Let's look at the Fibonacci numbers. The numbers are the followings. So if I write down the first 9 number of them, that will be starting from 0 and 1, and 1, 2, 3, 5, 8, 13, 21. So if we number the sequence with the x with the index, so calling the first one to be x0, and the next x1, x2, x3, x4, x7, x5, in this way, then we know that the first number x0 is 0, and then the second number x1 is 1, and these are like the initial conditions they are given, and then the rest of the numbers are generated following this relation. X at k plus 1, the next one will be the sum of xk and xk minus 1. So the next number is the sum of the previous two. And that holds for all the case going from 1 to 2, as long as you want. So, for example, now x0 is 0, x1 is 1, and then this number will be the sum of these two, and this number will be the sum of these two, and this number is the sum of these two, and this number is the sum of these two, and so on and so forth. So mathematically, we are interested in the question, that is, at what rate do these numbers increase, and how fast do they increase? And for example, is it possible to write out an expression for any number in the sequence, let's say x with the index 1000? So I repeat the highlight of the Fibonacci numbers here. And then we are now interested in finding an explicit formula for xk. And then, of course, we will go to matrices and vectors for help. So let's consider a vector vk, which is just collecting the two sequential number in the sequence. So it will be xk plus 1 and xk in this particular form. Then we see we can write out v0, which will be x1, x0, so it's 1, 0, these two here, and v1 will be x2, x1, which will be these two, and v2 will be these two elements, and v3 here will be these two elements, and so on and so forth. We can now rewrite this inductive relation here into this vector form. V at k, what would that be? That will be with xk plus 1 here and xk here. So then we can use the relation xk plus 1 is xk plus xk minus 1 and write it like that. And then we can express this vector as a product of the coefficient matrix times the unknowns involved. So we want to keep the unknowns with always the index here is 1 bigger than the index here. So we'll have xk here and xk minus 1 here. And then you can extract the coefficients. You will get 1 and 1, which we put here, and this will be 1 and 0, which we put here. And then this matrix here, 1, 1 and 1, 0, we'll call it A. then we have a relation. Vk is A times V at k minus 1. So this is an inductive relation for this vector form. Okay, so let's summarize. With this inductive relationship from our previous discussion on the vector product, we can conclude that by induction, the kth element here will be the matrix A to the power k times the initial guess V0. And here A is this coefficient matrix here. So from our discussion of the matrix power computation, we see that we need to diagonalize it. And then in the process of diagonalizing the matrix, the first step will be to find the eigenvalues and the eigenvectors of A. So let's carry on the computation of the eigenvalue. We form the characteristic polynomial by computing the determinant of A minus lambda I, and we get that. And then we can solve this quadratic polynomial to find the roots, and we find two of them, lambda 1 and lambda 2. These are the roots. Next, we carry out the calculation for the eigenvectors for lambda 1 and for lambda 2. So this is put it in lambda 1, and we need to solve this system, and then we find one solution, which is this one. And then for lambda 2, you put A minus lambda 2I times x equals 0, and you solve this one, and you get a second vector, which is eigenvector V2, which is like that. Okay, so since the calculation of the eigenvectors and the eigenvalues we have practiced many times, and please allow me to be brief here and just give you the result. Now, to diagonalize the matrix A, we will form a matrix we call P by collecting the eigenvectors. And we collect the eigenvectors, they are here. And that is an invertible matrix, and we can find the P inverse. By some calculation, you will have it. Then we know that from previous study that P inverse times A times P will be a diagonal matrix, where the diagonals are just the eigenvalues lambda 1 and lambda 2. So we put in our lambda 1, lambda 2, we get this matrix. And let's call this D. So once all these are computed, then we know that we can represent matrix A. We can kind of factorize it. A would be P times D times P inverse. And then the power of A can be quickly computed by the two P's, and the P inverse doesn't change. You just need to take the power of this diagonal matrix, D to the power K. Okay, so now let's put in all the expressions. So that's the P matrix. That's D to the power of K, where you just need to take the K power on the diagonal elements, and that will be the P inverse. Let's go back to the Fibonacci numbers from what we have computed. So we have computed now Vk would equal to A to the power of K times V0, the initial V. Putting the expression for A to the power K, we will have P D to the power K, P inverse times V0. Now let's write out the elements of these vectors. So Vk would be xk plus 1 and xk with as the element. And then V0 initially assuming that it's 1 and 0. Then we see that once this Vk is computed, then the kth Fibonacci number will be xk, which will be the second component of the vector Vk. So what one can do would be putting in the matrices P and D, K and P inverse and the initial vector 1, 0, and calculate these multiplications and work it out, and then take out the second element out of it. It's a bit lengthy of computation, but all the steps we know how to do. If you carry this out and you find the following, xk will take this expression. So we see that actually these are just the lambdas, right, the eigenvalues. So let's pose the question again. At what rate do these numbers grow as k grows very larger to infinity? Now, okay, so here's the expression again we had from the previous slide. And let's take a look at these two numbers. It's because it's their power of k that is expressing in the formula. So this number here, if you work it out, it's approximately 1.618034. And this number, if you take the absolute value, it is about 0.618034. They differ exactly by 1. And this number is strictly bigger than 1, and this number is strictly less than 1. So in particular, this number here, which you take the limit to the power k, and the k is growing, and it's less than 1, then you know as k increases, this number becomes smaller and smaller. And taking the limit, when k goes to infinity, this term here goes to 0. Therefore, we can say the following: xk equal to this expression, then as k becomes very large, this term goes to 0 and becomes smaller and smaller. And then at the same time, the first term has a rate here bigger than 1. So this one will be actually strictly growing, getting larger and larger. So this term eventually dominates, and this term becomes infinitesimally small. Therefore, for large k, you can approximate xk very well by just taking the first term here. And we can take a closer look at exactly how big will be the arrow. Let's take xk minus that term that we say will be a good approximation. So this will give us the arrow. What is the arrow? Well, that will be exactly this term that we say is very small, that we are neglecting. So the arrow is this red thing to the power of k. And we can evaluate this number for k equal to 1, 2, 3. And then you will find that for all those k's, this value here lies between -1/3 to 1/3. And in fact, you just need to figure out this number when k equals 1. Because when k becomes 2, 3, and 4, you know the absolute value of this one will be decreasing. Okay, so if you can show when k equals 1, this lies in this interval, then for the rest of the k, they also do. Okay, and that's not a difficult thing to show. Okay, now we argue. Since now xk is an integer, because it's a sum of starting from 0, 1, and then adding on to each other, and it's always an integer, so then it must be a unique integer, because we know xk would approximate this value here, and by an arrow from -1/3 to 1/3. Therefore, we need to just compute this expression here, and then find out the integer that is closest to this real number, and which is a unique integer. We can see it on the graph. So 0, 1, 2, you start from there, and then for some k, xk is here. And then you compute this expression here, and you find out it lies here. So this one will not lie right in between, in the middle between an xk to xk plus 1, because it's less than 1/3 in absolute value. Okay, so then the closest one to it must be the Fibonacci number in the sequence. Okay, so we repeat the formula here we have. Now let's calculate for a couple of k numbers. Let's say when k is 20. So if I compute this one to the power of 20, what do I get? I will get 6765.0 0.000295. Then I can safely declare that x20 will be the integer that's closest to this real number, which will be 6765. And now let's set k to be 25, and you calculate this number out. That's what you will get, 75,024.9999. And then you can conclude that x25 will be the integer closest to this real number, and that means that you need to raise this up to 5, and that will be the number. So it's 75025. Okay, so we see that the Fibonacci number increases with this ratio that is just one of the eigenvalue, lambda, that is 1 plus square root of 5 over 2. That's the ratio that increases. And this ratio here satisfies the equation that lambda equals 1 plus 1 over lambda. And this one is called the golden ratio. So you can say that Fibonacci number grow like powers of the golden ratio. So xk is approximately, actually very closely related to lambda to the k over square root of 5. Isn't that neat? I think so. So this concludes our discussion on the applications of the powers of matrices. And next time we will look into the topic of computing eigenvalues and eigenvectors, and possibly for a large matrix. Okay, so I hope you enjoyed today's lecture. I'll see you next time.